Today we need to revisit an old idea from chem study, the idea of movement of electrons in chemical reactions. A tool we're going to need to do that at the more advanced level is oxidation numbers. But first I want you to remember what we did in chem study. When we talked about movement of electrons in chemical reactions back in chem study, we looked at situations where we could very clearly see how the electrons were moving. For example, the rusting of iron. We start with iron and oxygen that are just in their non-charged atom/molecule form, molecule in the case of the O2. And when we get done with the chemical reaction, we have an ionic compound where iron has a +3 charge, oxygen has a -2 charge, and so it's very clear to see that in order for the iron to gain its +3 charge, 3 electrons have to leave each one of these iron atoms, and 2 electrons need to arrive at each of the oxygen atoms in order to give the oxygen its -2 charge. So we were able to draw some arrows and show how electrons were moving, and we laid down some vocabulary of electron movement, where reduction was a decrease in charge that was caused by a gain of electrons, and oxidation was an increase in charge caused by a loss of electrons. There are a lot of chemical reactions that move electrons that don't have as straightforward of a view of how the electrons are moving because we aren't necessarily always working with ionic compounds. Oxidation numbers are going to be our tool for tracking the movement of electrons when we don't actually have charged entities to work with. The oxidation number, or oxidation state, is the charge that an atom would have if all the bonding electrons were assigned to the more electronegative element in each bond. And in a few minutes, I'm going to show you how to look up electronegativity on your periodic table. The oxidation number is just a pretend number. It was something that chemists invented to help them kind of keep track of what was going on. Because it's not a real charge, it's not required to have a whole number like a real charge actually is. This idea of electronegativity makes it sound like this is going to be difficult to determine, but there's actually a pretty simple set of rules for determining the oxidation number. Sometimes science teachers use the term oxidation number or oxidation state incorrectly in place of the word charge, and that works out okay for ionic compounds because in that case the oxidation number really is just the same as the charge. The way I want you to think about the oxidation number is think about it as the actual charge, if there is one, like in ionic compounds, and an imaginary charge in a situation where there isn't one, like in molecular compounds. This is just going to help us keep track of electron movement in more complex situations. The rules for assigning oxidation numbers are on the sheet I gave you in class, and some of them are fairly obvious. The very first rule is that the oxidation state of an uncombined element is 0. That means when you're looking at something like O2, the oxidation number on oxygen is going to be 0 because the oxygen is in its normal state. It hasn't combined with anything else. Same thing is true for all the other elements on the periodic table, like zinc in just its normal metal form has an oxidation number of 0. Rule number 2 is essentially that if there is a charge, the oxidation number is the same as the charge. So if you see an ion like the calcium ion, the oxidation number on calcium is +2. Oxidation numbers traditionally are given charge followed by number as opposed to charge followed by number, as opposed to charge, which is given with number followed by charge. It's just kind of a convention chemists have set out to be able to tell whether we're talking about a charge or an oxidation number. Rule number 2 can also help us when we're dealing with ionic compounds. Within the ionic compound, we know that aluminum has a +3 charge, so its oxidation number is +3, and within aluminum oxide, oxygen has a -2 charge, so its oxidation state is -2. If you're looking at an ionic compound and need to assign oxidation numbers, the thing to do is just think about what the charges actually are. The rest of these rules, we're going to look at all the rules and then do a few more examples to go with them because they start to kind of interplay with one another. Rule number 3 says that in molecular compounds with nonmetals, hydrogen is going to be assigned an oxidation state of +1. Rule number 4, oxygen prefers to be a -2 in most of its molecular compounds. Then the important exception is when it contains the peroxide ion, which is the O2 2-, in which case each oxygen has to have an oxidation state of -1. Number 5 says that in binary compounds, the element with the greater electronegativity is assigned a negative oxidation state equal to its charge as an anion in its ionic compounds. If you look on your periodic table, you'll see that every element has kind of a dim number up here close to the atomic number. That's the electronegativity. Electronegativity is a measurement of how much a particular element wants to pull electrons close to itself when it's in a covalent bond. And we'll talk more about that in some of our later units. For now, we just need to be able to look up this number in order to decide which element has the greater electronegativity. Electronegativity is like selfishness. Basically, the greater the electronegativity, the greater the chances that an element gets to sort of have things the way it wants. You can continue to look these up on an as-needed basis, or there's a set of magic words to help you with the order of electronegativity for the most commonly used nonmetal elements. Our 3 magic words are fackeln, brisk, and spelled with a PH. This gives you the order of the most commonly used nonmetal elements in order from most electronegative to least electronegative. So it goes fluorine, oxygen, chlorine, nitrogen, bromine, iodine, sulfur, carbon, phosphorus, and hydrogen. Rule number 6. For an electrically neutral compound, the sum of the oxidation numbers must add up to 0. And number 7, for an ion, the sum of the oxidation states must equal the overall charge. These rules get applied kind of in a hierarchical order. You basically always start at the top, work your way down, and the very first rule you come to that gives you an answer is the rule that you're going to use. So we're going to look now at a handful of examples here, starting with the compound carbon dioxide. If I need to assign oxidation numbers to the elements in carbon dioxide, I start at the top of my rules, and the first rule I come to that seems to apply here is that oxygen prefers to be a -2. If oxygen is going to be a -2, and the entirety of this compound has to add up to 0, with it being CO2, we've got a -4 for the oxygens, and therefore the carbon ends up having to have an oxidation state of +4, because we have 2 -2s and a +4 to add up to 0. If we look at something like sodium sulfate, the first rule we come to says that if something is an ion, its oxidation number is the same as its charge. Since sodium sulfate is an ionic compound and sodium is a +1 ion, we start by assigning sodium to be +1. Working down the list, the next useful rule we come to is that oxygen prefers to be -2. Now on the whole, we need to make the charge of this compound add up to 0. So for the oxygen's portion, we have a contribution of -8. And for the sodium's portion, we have a contribution of +2. And if we need the whole entire thing to add up to 0, that means that the sulfur here has to contribute +6 to our situation. Our next compound is the first place that we have to invoke. Oh no, I guess we really don't. We still have oxygen here, so we don't have to invoke rule number 5. So here we're just going to continue to use oxygen kind of as our guide for how to get things done. This is a molecular compound consisting of sulfur and oxygen. Oxygen prefers to be -2. That means that the oxygen piece of this is a -6 up here. which means that the sulfur has to contribute a positive 6, and that positive 6 gets shared by the two sulfur atoms here. And so we pretend that each sulfur has a charge of positive 3, and we pretend that each oxygen has a charge of negative 2. Now remember, those aren't actual real charges because this is a molecular compound, and we know that molecular compounds get together with the atoms in their neutral atomic state, not in their ionic state. One of the characteristics of nonmetals is that they can actually have a wide variety of oxidation states. So if we look at another of sulfur and oxygen's compounds here, in the SO2, oxygen has an oxidation number of -2, and that's going to force the sulfur to have an oxidation state of +4. So you can see here sulfur is +3, but then later sulfur is +4, and that's characteristic of our nonmetals, that they can have variable oxidation states. Our next one, we have potassium. This is an ionic compound with a metal and a nonmetal. And in its ionic compounds, we know that potassium has to be a +1. And here's a situation where, for the first time, we have to deal with oxygen in a different possibility here. If potassium has to be +1, because that's the only state it can take on, that means that our oxygen here isn't going to get to be what it normally likes to be at the -2. Oxygen has to take on its other possible oxidation state, which is its -1 oxidation state. The O2 here is serving not as as two oxide ions, but serving rather as the peroxide ion, the O2 2-. In nitrate, we have nitrogen and oxygen. This is a case where oxygen does get to have its preferred state of -2, so we assign the oxygen a -2. But now we have a polyatomic ion. At -2 each, the oxygen ends up contributing -6, but the whole ion has to have a -1 charge, so that means that our nitrogen is +5, because +5 plus -6 gives us a -1. Here we have some ammonium sulfide. It has nitrogen, hydrogen, and sulfur. And so we have to start by noticing that this is an ionic compound. An ionic compound, sulfur is acting as the sulfide ion, so it has its charge of -2. And then within the ammonium ion, hydrogen is bonding to a nonmetal. So hydrogen takes on its +1 oxidation state. And then we have to make the whole entire thing add up to 0, or you can think of it as making the ammonium ion add to +1. You'll come up with the same answer either way. But as we look at this, we see that our sulfur is contributing -2. Our hydrogen here, there are 8 of them, so the hydrogen is contributing a +8. So the nitrogen has to contribute to this overall situation a -6, and that -6 is shared between the two nitrogens. So here's a case where the nitrogen takes on the oxidation state of -3. Our last example is phosphorus pentachloride. And this is the first case where we have to invoke this rule that in binary compounds, the element with the greater electronegativity essentially gets to have its way. So as I look at phosphorus and chlorine, chlorine is the more electronegative element. Chlorine's favorite charge is -1. So it gets to be -1, and in being -1, that forces phosphorus to be +5. From here, you have some oxidation number practice that I would like you to complete. And as you complete that, you're going to do question number 1, and then stop, check your work on question number 1 to make sure you have the right idea, and then you're going to complete question number 2.